My name is Joe Spadola. I am an applications engineer for HPM nCode, and I am actually based out on the West Coast. Today's webinar is called nCode for Fatigue and Durability Analysis. And the purpose of today's webinar is to do a couple of things. First, we want to give a brief introduction to fatigue theory. And when I say brief, I mean very brief. We've got, a full day class that we teach about fatigue and durability, and what I'm going to be talking about today is a half dozen slides. So brief is it's going to be very brief. So it'll just be a very standard introduction to fatigue theory, but hopefully it'll provide some motivation for what we're going to be doing later. And then secondly, we're going to learn how to perform fatigue calculations with nCode GlyphWorks and DesignLife. Those are two products that nCode has, and we'll be actually doing a live demonstration of both of those in the process of this webinar. So the agenda is going to look, or it does look, something like this. Again, first we're going to give a quick background on nCode as a brand. I'm going to introduce some of the products that we offer, including two of the ones that we'll be seeing later in the webinar. I will then give a brief, again, very brief introduction to fatigue theory. And then I will give an introduction to performing test-based fatigue calculations. So this would be taking measured strain gauge data and processing that data to come up with fatigue calculations. And that will be done in a software called GlyphWorks. After that, I will introduce the concept of performing finite element-based fatigue calculations. And the idea behind this is that we can take a solved FEA model that has stresses. We can define how those stresses change inside DesignLife and come up with a fatigue plot. Basically, we're turning a stress plot, which we get from FEA, into a life plot that we generate with DesignLife. And then it'll be followed by a software demonstration where I'll be showing how to perform both the test-based calculation and the FEA-based fatigue calculation in GlyphWorks and DesignLife. And then at the end, we'll follow with a short question and answer session. So nCode as a brand has three different products. Two of the products we'll be talking about today are highlighted here in yellow. The first one is called GlyphWorks, shown in the middle here. And GlyphWorks is a data processing system for performing fatigue calculations and operating on all sorts of measured test data. I'll be highlighting that in a little bit more detail in just a second. Excuse me. A second product that we have is called DesignLife, and DesignLife is it's also a system for performing fatigue calculations, but it's based on FEA models, solved FEA models. And I'll be highlighting a little bit more of its capabilities here in just a minute as well. The third product we have that we're not going to be talking about at all today is called automation. Automation is you can think of it as a database where you can store and manage all of your test data. But GlyphWorks interacts with automation, so you can have as data is automatically uploaded to your automation server, GlyphWorks will see that data and then process that in any way that you choose. You build the analysis processes beforehand, you load them up onto the server, and then when your data hits the server, you can process that data automatically and have dashboards of results sent back to all the users. Again, today we're not talking about automation. We're going to be talking about GlyphWorks and DesignLife. So to give a little more in-depth explanation of GlyphWorks, GlyphWorks again is a suite for processing test data. We have lots of data visualization capabilities, lots of ways to just look at data. We can also report data in an automated way. We can perform lots of signal processing, basic filtering, mathematics, editing, stats. Even, you can record a GPS channel with your data as well, and see how things change, or your, the characteristics of your accelerations or strains or whatever you're recording. Not only how they happen in time, but you can tie it together with GPS as well to see how it happens spatially as well as in time. We also have automated detection tools that'll allow you to highlight spikes and flat lines and drift and any other sort of anomalies that you might find in data. We also have a wide range of fatigue analysis capability tools. Some of them, well, one of them I'll be highlighting today. We can do stress life, strain life, crack growth analysis, and this is all tied together with the basic digital signal processing, so you can condition your channel and then perform your fatigue analysis all in one process. We also have the ability to accelerate vibration shaker profiles, where you can use tens to hundreds of hours of measured test data, and you can then create a shaker profile that will replicate the failure mechanism and damage of that test in a much shorter period of time. Okay, so we're literally accelerating shaker table tests. We also have a suite of noise and vibration capabilities for working with rotating machinery. We can do octave analysis, frequency response functions. We have whole body weighting analysis as well. That's just a small subset of what GlyphWorks can do, and later we'll be looking at, in particular, the strain life fatigue calculation. Design life. Design life is a way to bring in solved FEA models and turn the stresses that you see in FEA into damage plots or life plots. So what we're doing is predicting fatigue from FEA. We can perform stress life, strain life. We can look at temperatures as well. We can model plasticity, look at stress gradients. Lots of built-in features there that enabled you to perform a quite detailed fatigue calculation. We can look at vibration, which is just doing fatigue in the frequency domain. So instead of supplying a time history, you'd be supplying a PSD. It's essentially a virtual shaker table that we can simulate. We support all the major FEA codes: ANSYS, Abacus, Nastran, LS-DYNA, and there's a few others as well. Like I said earlier, this is extremely highly configurable. It's very easy to use. You'll see as I use it later. It has a very simple drag and drop user interface, but you can get down into the nitty-gritty details of all of the calculations and change those settings to make sure that you're running it exactly the way that you need to run it. Okay, so let's get into the meat of today's topic, fatigue and durability. So what is the importance of durability? Well, we're all here probably as engineers or analysts or designers because we designed something, or we have some part in designing something, and we want to know what happens to that in the real world. We design something and we put it out into the marketplace. People use it. We want to know that, not only how it's being used, but that when it's being used by people in the real world, that it's going to be used, or that it can be used for the amount of time that we design it for. We don't want to have a significant amount of parts come back prematurely. So the whole point of durability is figuring out how our part performs over a very long period of time. Okay, so we can then ask ourselves another question, and that would be, what is fatigue? So we've talked about it. We know that it has to do with parts, lasting for a certain period of time. We want to know how things perform over a long period of time. So let's define that from a physics standpoint. What is fatigue? Well, if we look it up in a dictionary, we might see something like this first definition here at the top. Weakness in a metal or other materials caused by repeated variations in stress. Okay, pretty simplistic explanation, but the key point here is that it highlights the fact that there are repeated variations in stress. Okay, fatigue is all about changing stress. If we apply a static load and hold it forever and the part fails, that has nothing to do with fatigue. Okay, that's a different failure mechanism called creep, and that's not what we're talking about today. Here we're talking about repeated variations in stress. That change in stress is critical to fatigue. If we look up the definition in slightly more technical text, perhaps a textbook or something, we might see a definition like the second bullet point here, where it says the initiation and subsequent growth of a crack or growth from a pre-existing defect until it reaches a critical size. So again, the keys here is that fatigue cracks are caused by cyclic loading. Okay, we need those stress cycles in order to drive fatigue as a failure mechanism. The subtleness of fatigue comes in the fact that our part can fail even though the stresses aren't that high. Okay, so it's a progressive failure. It happens over a long period of time, typically, and they start to grow from very small defects in the microstructure of the material, and they then propagate into large cracks, and ultimately the entire part fails suddenly. So when we think about structural failure, the first thing that usually comes to mind is just a simple static failure. So if we look at this top plot here, we're looking at the behavior of a material as it's failed under a single pass. So this would just be a standard tensile test. If we look at the stress strain plot there, if we follow the red line up all the way through the dotted line, we see that there's this linear portion of the stress strain curve. Okay, this is when stress and strain are linearly related through Young's modulus. At the point where it starts to curve a little bit, that's when yielding occurs. And if we continue to pull and apply force to our part, we start to see large strain changes for relatively small stress changes. And if we continue doing that, the part will ultimately fail when we reach our UTS, or our ultimate tensile strength. So that's static failure. Most people are familiar with that. Static failure is easy to design against for the most part. Fatigue is slightly more subtle, like I mentioned earlier. If we look at this bottom plot here, we know that fatigue occurs over a very long period of time. This squiggly line here, this red squiggly line down at the bottom, is showing what I mentioned earlier is the primary driver of fatigue as a failure mechanism, this repeated stress variation. So if we have a stress history that looks like this red line here, if we keep doing this for a really long period of time, our part may eventually fail. And if we think about how those stresses, or how high those stresses are going, if we look up on the stress strain curve, we can have a relatively low stress. Okay, in this case, you can see we're not even exceeding yield, but we're still seeing failure over a very long period of time. Okay, so that's kind of the subtlety in fatigue, is that even without high stresses, as long as those stresses are constantly changing and we're cycling back and forth, we can still see failure occur over a long period of time. These stress cycles that I'm talking about, these fatigue cycles that I'm talking about, each of them are going to be unique, and they have some important, if we think about just one simple cycle, each cycle, as is shown here by this red line, has a couple important factors. So we've already established that fatigue and crack growth are driven by cyclic loading. So let's just look at one single cycle and see if we can pick out some important factors from that. The most important factor in a fatigue cycle is this delta S that you can see on the right, the stress range. And that's nothing more than the maximum stress of the cycle, the difference between the max of the cycle and the minimum value of the cycle. Depending on what textbook you're looking at or what kind of SN curve you're looking at, some people might report not delta S, the stress range, but instead the amplitude, which is represented here by SA. And SA is nothing more than half of the stress range. So it's just something to keep an eye out for when you're looking through fatigue material, fatigue textbooks or whatnot. The second most important factor is going to be the mean stress. And you can see that is literally just the mean, the average of the max and the min. The mean stress is the second most important driver in fatigue. We're not going to go into why that is today, but I just wanted to make mention of that. Today, the only thing that we're really going to look at is the delta S, that stress range. So these fatigue cycles, as they occur, they cause some amount of damage to the part. Okay, and the things that we care about, one, we already know the cycle size. So how much did that stress or strain change? What is that delta S that we looked at earlier? Okay, the peak stress alone is not enough information for us. Okay, we need to know the change in stress, because that ultimately, that delta S, that's what's driving the fatigue. So not only do we need to know how large a single cycle is, but we also need to know how many of those occurred. Were they all the same size? Were they large cycles? Were they small cycles? Was there a whole bunch of large cycles? Was there a whole bunch of small cycles? We need to know that information in order to figure out how long a part's going to last. Okay, how big were the cycles and how many were there? We can use a bank account analogy to think about this concept of fatigue damage. Okay, so we know each cycle contributes some amount of damage to the part. So you can think of damage kind of as a principal amount in your bank account. So if you have a principal amount in your bank account, you go through life and you have various expenditures. Okay, you're spending money on a mortgage. That's a large expenditure. You're spending money on your cell phone. That's a medium-sized expenditure. You're paying for lunches and dinners. These are relatively small expenditures. So the idea is all of these expenditures are exhausting the principal amount in your bank account by some amount. Okay, it doesn't matter how big the expenditure is, you're just withdrawing from that principal. Okay, and over time, all of these cycles, all of these expenditures, whether large or small, are ultimately depleting the amount of money that you have in your account. Okay, when all your money is gone, you're broke. Okay, no pun intended there with the fatigue damage analogy. So damage is thought of as kind of the same thing. So you've got this fixed amount of damage that you can expend from your part. When that damage exceeds a certain value, which turns out to be 1, then your part is considered to be broken. Okay, so if we think of an SN curve, let me skip through this real quick. This is what an SN curve looks like. So it's generated by breaking a series of test specimens that are plotted in log-log space, and then we simply fit it with a straight line. The definition of that line is shown here on the top right. SA equals sigma f primed nf to the power of b, where sigma a is that amplitude. So in this case, it's half of the range that we were talking about. That's usually what we are given in terms of a fatigue cycle. We know what that amplitude is. sigma f primed, that's the intercept of this fitted line through the y-axis. Okay, so that's a material property that can only be gathered it can only be gathered by doing actual fatigue tests. NF, that's the number of cycles that the part is predicted to last given a certain amplitude. That's what we're usually trying to solve for. And then this raised to the power of b. B is just the slope of this line. So that equation there is nothing more than the equation of a straight line in log-log space. So see, it would be the equivalent of y equals mx plus b in standard coordinates, but here we're looking at log-log space. So that is the form that the straight line equation takes. And again, what we're typically given is SA. So we find all of the cycles in our stress history. We know what a stress amplitude is. Then we simply look up that amplitude on the y-axis here, trace it over to the intercept of that curve, and then look down onto the x-axis and see what value that is. And that would be how many cycles can occur at a given stress amplitude until failure is predicted to occur. Okay? So that is fatigue theory 101, an absolute beginner's introduction to fatigue theory. If you're interested in learning more about that, I suggest taking a look at our list of webinars on our website or events. We do a lot of seminars around the country where we spend an entire 8 hours talking about fatigue theory. So if you're interested in learning more about that, check out our website to see if you can find some more information about that. For now, I'm going to continue on, and now we're going to look at doing fatigue analysis on measured strain gauge data. So the concept here is that we're going to perform a fatigue calculation. We're going to measure a structural response with strain gauges. So we're going to have an actual physical prototype. We're going to put a strain gauge on it, and we're going to assume that we're putting that strain gauge in a critical location. Okay, so the advantage of doing it this way, the test-based method, is that it's relatively easy and it's accepted historically. We've been doing this for a long period of time. People have a lot of experience with it, and it's a relatively accepted approach. We also know that strain gauges will record strains wherever they come from, whether it's linear, whether it's nonlinear, whether it's due to some sort of thermal effect. Whatever the strains, whatever strains our part sees, these gauges will pick up, whether that's good or bad. Maybe you don't want to capture strains due to thermal effects. Maybe you do, maybe you don't. That's up to you as an engineer to decide. But the strain gauges will record those. Disadvantages here is that doing the test-based approach, we need to place those with care, right? We have to make sure that they're oriented properly. We have to make sure that they're adhered properly, that we're getting good readings off the gauges. Also, we need a hotspot for each gauge. We can't just put a strain gauge on the middle of a part, do a fatigue calculation and call it good. We need to make sure we're capturing the peak strains on our part, or at least as close to the peak strains as we can, in order to get and that location that we put it is a location of interest. By doing this on a physical prototype, our part or our data will have a limited shelf life. If we change the design, the data that we have originally recorded doesn't really apply anymore. If you change the material, our strains are going to be different. If you change how you bolt the thing together, our strains are going to be different. If you change fillet radii, things are going to be different. So it has limited shelf life, and that is a downside to this. The other obvious downside is that you do need a working prototype. So you need to spend the manufacturing time and money to actually come up with a physical prototype. Okay. So I'm going to go ahead and jump into the software and do a demonstration of this. So this is nCode. I can access GlyphWorks by clicking on our GlyphWorks app over here. And the first thing that pops up is the user interface here. On the far left, you will see what we call the available data window. This is where, when I first started GlyphWorks, I did this before you guys saw it, but it asks you to point to a working folder. All the available data is a list of all the files that GlyphWorks recognizes in that working folder. Okay, so we'll see things like in the time series folder here, this will be any time series data that GlyphWorks recognizes. Okay, I can bring data onto this grid paper in the middle, which we call the workspace, by simply dragging and dropping that data onto the workspace. Okay, I can then display that and maximize this view so that you can see all of that data in all its glory. Once we're in this view, you can zoom in, you can pan left and right. So you can pan left and right. You can overlay the data. You can separate it again. You know, anything that you might expect to be able to do while looking at data of this kind, you can do. These are fully interactive plots, and you can manipulate them in quite a number of different ways in order to view the data. Okay, so I'm going to minimize that. So I have my data on my workspace. I want to build an engineering process that calculates the fatigue life from these measured strains. Over on the right, we have what we call the glyph palette. The glyph palette is a collection of engineering functions, and a glyph is nothing more than a single engineering function. We have a series of basic DSP glyphs. These glyphs allow you to do things like filtering, differentiation, calculate statistics. We have tools that allow you to calculate derived channels based on existing channels. We can calculate frequency spectra, look at PSDs. Lots of digital signal processing tools available in here. We also have a series of other glyph palettes, like the frequency palette, which allows you to work with things in the frequency domain. You can do joint time frequency analysis, waterfall analysis, other types of filtering, frequency response analysis. So all of those tools would be in this sort of toolbox. For now, I'm going to want to do an actual fatigue calculation, so I'm going to go to my fatigue palette. I see that I have a strain life glyph, or strain life engineering function here. I can simply, in the same way that I got the data onto the workspace, I can simply click and drag and drop my strain life glyph onto the workspace here. Okay, so now I have my input data. I've got some strain life calculation going on here. I'm going to want to view the results of this data in some way. So over on the right, I've got a display palette that will allow me to do that. I'm going to view a number of things, so I'm just going to pull some displays onto the screen, and then I'll run the process and we can walk through it. I'm going to view a histogram display, and then I'm going to want to look at some metadata results. So I've got all these glyphs, all these functions on my workspace here. In order to create my process, I simply have to send the data between all of the glyphs. So this is my input data. This is where everything starts. I can send data from this glyph to my engineering or to my strain life glyph by simply clicking on these output pads. As soon as you click on the output pad, you can see that a pipe is connected to your mouse. Okay, I then simply click on the input pad that I want to send that data to. So here I'm taking my recorded strains, my strain histories, and I'm sending them over to my strain life calculation glyph here. Okay, the results of that calculation are then sent out of the right side of that glyph. So you can see I have quite a few output pads here. They do a number of different things. For today, I'm just going to highlight a few of them. One thing I'm going to look at is the rainflow histogram, and I'm going to send that to my histogram display. I'm also going to look at something called the damage histogram, and we're going to highlight these or look at all these in just a moment. I also want to look at the results of this calculation, so I'm going to connect that up there. So at this point, I'm almost ready to go. I've got my input data. my recorded strain histories, I've got my strain life calculation here in the middle, and then on the right side, I've got a couple displays that are going to allow me to view the results of this calculation after it's complete. The only thing that I need to do here for a fatigue analysis, if you remember a few minutes ago, we were looking at some fatigue theory. In order to calculate how much damage is occurring in these strain histories here, I need to assign a material property or a material curve to this data. So I do that by accessing the properties of this glyph, simply right-clicking on it and going to my Materials tab. We have a wide range of built-in materials available to you. I'm not going to highlight all of them right now, but there are several hundred of them in there standardly. For this example, I'm just going to take a standard carbon steel and click OK. So now I've assigned my material property. I'm ready to run this process. To do so, up on this top toolbar here, I can see that there's a Run button. So if I simply click that Run button, the process will commence. It happened pretty quickly, but you can see data was sent from the input glyph through the strain life glyph, and then after it was done calculating, it sent the results out to these to the result displays here. So let's take a look at the first result. This is showing me two things. One is a histogram display, or a rain flow histogram, okay, on the top here. So this is showing me a distribution of the cycles that it found in each of the channels. In this instance, we're looking just at channel 90 right now, so that was one of the channels included in the test that I've just ran. It contains, let's see if I can look at these. These are completely interactive views, so I can move them around in any way that I want. Typically, these are looked at from a top-down view, so I can simply click on the top-down view there. Here I've got on the top my rain flow histogram. This is showing me the distribution of range. Okay, you remember we talked earlier, the most important factor in fatigue is the range of stress. In this case, we're looking at strain, so the strain range for particular cycles, and that's what this axis is showing me here. Okay, the second one, the second most important factor is the mean stress, and that's what's shown on this axis here. So this is just showing me a distribution of the range and mean of cycles that I have. Okay, we know that the larger the range, the more damage that occurs. So the cycles that we see way up here on this end are the most damaging cycles. This plot down here is showing me what we call the damage histogram, and that is simply a collection. So these are cycles as well, but the cycles that it's showing here are the cycles from the rainflow histogram that actually caused damage. Okay, these cycles way down here, where you see this heavy collection of cycles, those are really, really small in range. Okay, they're so small, in fact, that they don't even cause any damage. So there's a whole bunch of those guys. The good thing is none of them cause damage, so it's not going to be a problem for us. What we can see, though, is that there are quite a few that do cause damage. Okay, so this is a unique way to characterize what kind of signals, or sorry, what kind of cycles are present in your input channel, and then what kind of those cycles, which ones are actually causing damage. And the Z value here on this plot is the amount of damage that occurred. Now, you saw I ran about half a dozen channels through the analysis. I'm only looking at one channel here. If I want to look at the rest, I can simply scroll through all of those. Okay, so it's a multi-channel in, multi-channel out process. Okay. Another thing that's useful to look at, of course, is life and repeats. Life is just the inverse of damage. So here we're just looking at how, on a per channel basis, how long various channels are predicted to last. So here we're seeing channel 90 is expected to last about 17,000 repeats until a crack is predicted to initiate at that location. And you can see that we have a readout for all of those channels that were sent in. Okay, so that's GlyphWorks Fatigue in a nutshell. It does quite a few other things, and you can set all sorts of properties in the strain life glyph. But that's just a very simple rundown of how it works. Okay, so again, these are the advantages of using GlyphWorks to perform fatigue calculations. I'm not going to read through them all right now. It's kind of just there for your reference. So the second thing I'm going to talk about today is performing FE-based fatigue analysis calculations. So the idea here is that we're going to use solved FEA models to predict stresses and strains. Well, we're going to use FEA tools to predict stresses and strains. We're going to take those stresses and strains that FEA solved for us, and we're going to then use design life to determine virtual stress cycles. Okay, so we're taking static stresses from FE and using design life to cycle those stresses. And we're doing it on a full model basis. So we're getting we're taking stress plots and turning them into full model life plots. Okay, the advantage here is that we don't have to have a prototype. It's easy to address design changes quickly. We've been doing FE for quite a while, so it's an accepted method for doing structural analysis. And we have a wide variety of solutions from FE. We can do nonlinear or linear. We can do statics. We can do dynamics. We can look at frequency response. So there's a wide-ranging list of capabilities available. The downside is that we have to ensure that the stresses we're getting out of FE are reasonable and are correct. If we're going to perform a fatigue calculation, we didn't go into the details of it, but small changes in stress can equal large changes in life. So we need to make sure that the stresses we're getting out of FE are accurate. Okay, and that is not always an easy thing to do. So let's jump into a design life calculation right now. So I'm going to go back into the software. And this time I'm going to jump into design life. Okay, and in the same way that GlyphWorks recognized time series files, design life recognizes FE models. Okay, so I've got my FE model, my solved OP2 file. This comes from Nastran. I can simply drag and drop it onto the workspace. I can display the model, and I can view that model. Here you can see it looks like I've got some shells on this model. I'm just going to turn the solids off so that I can look at just the shells. So there's my model. It's a relatively simple shaft model. And again, this came from FE. So I have to, at this point, I already have to have my stress results in here. And I can view some of those stress results by looking at the result cases that are in there. Okay, this particular model has two independently solved stress cases. One you can see here is simply a bending case. So I've held one end constant and I've applied a force in the vertical Z direction. Okay, and the resulting stresses are shown right here. Now, design life hasn't done anything unique yet. This is all from Nastran. Okay, we have a second load case in there, and that second load case is a torsion case. So here I've held the same end constant over here and then applied a torque in the X direction. Okay, so those are the two FE load cases. What we can do now is, in the same way that we performed a fatigue calculation in GlyphWorks, we can do that in design life. So I'm going to go to my design life palette here. We have a wide range of design life tools available to perform calculations with. As I mentioned previously, for now I'm just going to use the strain life CAE fatigue tool. It's going to allow me to do a strain life calculation based on this FE model. So in the same way that I looked at data, or that I sent data through the through the process in GlyphWorks, I can do the exact same thing here in design life. So I'm going to send my FE model to my EN, or to my strain life calculation tool. Similarly, I'm going to have a couple display options available to me after that calculation is done. So I'm going to go to my display palette again, and I'm going to bring in FE display. So look at my finite element display. And I'm also going to look at a data values display. Okay, so I can send those results to that plot there. So there are two things that I have to do here. Since I have static loads, I have to define how those loads are changing. I also need to apply a material property to this model. So first thing I'm going to do is apply a material property. I can do that by editing the material. We call it material mapping. So very similar look to the way that I applied the material property in GlyphWorks. In this case, I'm going to grab the same material, and I'm just going to drag and drop it onto to my model. Now, if you have different element sets and whatnot, you can apply different materials to different element sets. I'm just going to apply this to the entire model since it's a very simple case here. I'm going to say OK. And the second thing I have to do is define how these loads are changing. So I have a bending load and I have a torsion load. I happened to actually take measurements in the field of the vertical loads and the torque loads. So in this part here, I know that my vertical load is applied in this positive z direction. So I actually went out into the field and I recorded what happened, or the loads that were occurring over time in that positive z direction. At the same time, I recorded the loads that occurred, or I guess the torque loads that were occurring. And that recorded data has been saved in this DAC file, or this time series file here. So I can bring that onto the workspace, and I can view that data. So here's the corresponding vertical load on that shaft. Okay, it's about 7 or so seconds, so it's a relatively quick test, but it corresponds to some event that I went and recorded in the field. I have a corresponding torque load that has been applied as well, or that has been recorded, sorry, as well. And what I'm going to do now is use design life to calculate the fatigue life of this part here that has been subjected to these load histories. Okay, so I'm simply going to send this data into my my time series input, or the input on my analysis glyph. So I've got my input geometry. I've defined how my loads are changing, and I've applied a material property. At this point, I'm ready to run the process in the same way that I ran the GlyphWorks process. So I can simply click on the Run button here, and it will pump through the calculation. The result then is a, zoom out a little bit, is a fatigue life contour plot. Okay, so you saw the stresses I had previously. That was all done in FE. What I've done is taken those stresses and determined how they change, okay, with those input files that I used, with the time series files that I used. I defined how those changed and done a cycle count, looked at the SN curve, and I've done that for every single node in this model, okay? And the result then is a, in this case, I'm looking at damage, so I can actually look at the inverse of that, which would be the life. And now I can see something that might make a little more sense in terms of data over here. So I see that the minimum life, okay, the minimum life is about, what, 370,000? So that means I can do about 370,000 repeats of whatever event that time series history corresponded to. Okay, and it's telling me that the minimum life is going to occur at this particular node right there, node 52,684. Okay, and that's likely going to be in this hotspot right here. Okay, so that's a very simple rundown of design life and how we can use measured load histories to scale static loads that we've calculated in FEA. One other thing I'll show you real quick. I told you that we can look very simply at the life plot on the life contour plot, but here we also have a rundown of, let's make this a little bit bigger. On a node-by-node basis, we can see the life, we can see the damage, we can see some other information as well, like what material group did that come from, what was the property ID, material ID, what was the dominant stress direction. So lots of other information that we can see here as well. Okay, so that's a very quick rundown of design life. So I'm going to go back to the presentation real quick. And again, in a similar way that we mentioned the benefits of performing fatigue calculations in the test-based world, we have a similar list of benefits here in the FEA world. and they're kind of here again just for your reference. I'm not going to focus on them too much.